Hi everyone, this is Hossein from EJ Academy. In this video, we wanted to talk about interest that is compounded continuously. In the previous videos, we talked about simple interest and compound interest, and also we talked about accounts that pays interest which is compounded annually, quarterly, and monthly, and we obtained an equation that gives us the total balance in the account after a certain number of years. That equation was F equals P times 1 plus I divided by M to the M times N. In this equation, N was the number of years, P was the principal, F was the total balance after n years, I was the annual interest rate, M was the number of compounding periods per year, and the whole I over M ratio was the interest rate per compounding period. If you want to check those videos, I have left their links in the description below this video. If the interest is compounded annually, M is equal 1 because the interest is paid to the account once every year. If it is compounded quarterly, M is equal to 4, and if it is compounded monthly, M is equal to 12. Now in this video, we wanted to see what would be the balance of the account if the compounding period is continuous. If interest is compounded continuously, M approaches infinity, and we wanted to see how much would be the balance of the account in this case. Let's use the equation above to calculate the total balance in the account after n years in case of the interest that is compounded continuously. So the equation was F equals P times 1 plus I over M to the M times N. And because M approaches infinity, we need to take the limit of F when M approaches infinity equals limit when M approaches infinity. And pay attention that in this equation, P, I, and N are constant. And the only variable is M. And since P is constant, we can take it out of the limit. So we have P times limit, open parenthesis, 1 plus I over M to the M times N when M approaches infinity. If we replace M with infinity, we would have P times 1 plus I over infinity to the infinity times N. I over infinity approaches 0, and infinity times N approaches infinity. As a result, we have P times 1 to the infinity. And this is an indeterminate power. So in this case, we use L'Hopital's rule to calculate this limit. Let's assume y is equal to 1 plus I over M to the M times N. Now we take the natural logarithm of both sides. So we have ln of y equals ln of 1 plus I over m to the m times n. And if we simplify this, we get m times n times ln of 1 plus I over m. As a side note, ln of a to the b is equal to b times ln of a. And this is the rule that I use here to simplify this equation. Now I take the limit of this expression when m approaches infinity. So limit when m approaches infinity, ln of y equals limit when m approaches infinity, mn times ln of 1 plus I divided by m. Now I'm going to rewrite this expression in such a way that this mn multiplier appears in the denominator. So I'm going to have limit when m approaches infinity. This is my fraction line. So I have ln 1 plus I over m in the numerator, and the denominator would be 1 over mn. And when m approaches infinity, this fraction approaches 0, and this 1 over mn approaches 0 as well. So I'm going to have ln of 1 over 0, which is 0 over 0. And because I have 0 over 0, I can use L'Hopital's rule. And as a reminder, whenever you have a limit of f of m divided by g of m when m approaches infinity is equal to 0 over 0 or infinity over infinity, then this limit of f of m divided by g of m when m approaches infinity is equal to limit of f prime of m, the first derivative of f, divided by g prime of m, the first derivative of g, when m approaches infinity. And this is the L'Hopital's rule. Let's go ahead and apply this rule. Let me copy the expression and bring it down. So what I have in the numerator is my f of m. So this is f of m. This 1 over mn is the g of m. This limit equals limit of f prime of m over g prime of m as m approaches infinity. Before continuing, I wanted to write few reminders on the side. Whenever you have ln of u, where u is a function of x, then the derivative of ln of u is equal to u prime divided by u. Also, whenever you have 1 over u, where u is a function of x, then the derivative of 1 over u is equal to negative u prime divided by u squared. Now let's get back to the equation and apply these rules. We have limit as m approaches infinity. On the numerator we have the derivative of 1 plus I over m divided by 1 plus I over m, and in the denominator we have negative of the derivative of mn divided by mn squared. Let's continue by simplifying the above expression. We have the limit as m approaches infinity. In the numerator, we have to take the derivative of 1 plus I over m. I'm going to write it down on the side. 1 plus I over m. Taking the derivative with respect to m is equal to 0 minus I divided by m squared. Okay, let's go back to the limit expression, and in the numerator we have negative I divided by m squared over 1 plus I divided by m. In the denominator we have negative n divided by m squared n squared. And in the denominator we can simplify this expression. This n cancel out with n squared in the denominator, and we have n in the denominator. Let's continue. We need to simplify this fraction. As a reminder, if you have a fraction a over b divided by another fraction c over d, you can rewrite this as fraction a over b times the reciprocal of c over d, which is d over c. So we're going to use this to simplify our fraction here. So we have the limit as m approaches infinity. The first fraction is negative I divided by m squared over 1 plus I divided by m times the reciprocal of the denominator, which is m squared n divided by negative 1. This negative 1 here and this negative sign here cancels out, and m squared here and here cancels out, and what we are left with is the limit as m approaches infinity. We have a fraction. In the numerator we have I times n, and in the denominator we have 1 plus I divided by m. And when m approaches infinity, I over m approaches 0, and as a result this limit is equal to I n divided by 1, which is equal to I n. As a result, limit of ln of y as m approaches infinity is equal to I times n, where y is equal to 1 plus I divided by m to the m times n. But what we are interested to calculate is not the limit of ln of y, is the limit of y as m approaches infinity, and we still don't know this value. And to remind you, we started with this total balance f is equal to p times 1 plus I divided by m to the m times n, and for the interest that is compounded continuously, m approaches infinity, and that's why we needed to calculate the limit of this expression here, and we defined this expression here as y. We replaced it with y. So far we calculated the limit of ln of y. To calculate the limit of y, we need to use this property of natural logarithm. Assume z is equal to ln of y, which by definition is equal to log of y with the base of e, and then we have e to the power of z is equal to y, and since here we define z as ln of y, we replace it and we get e to the power of ln of y is equal to y. So we use this property to calculate the limit of y here. So the limit of y as m approaches infinity is equal to limit of e to the ln of y as m approaches infinity. And we have already calculated the value of ln of y as m approaches infinity, which is I times n. And as a result, the limit of 1 plus I divided by m to the m times n as m approaches infinity is equal to e to the I times n. And we replace this into this equation. If we do that, we get the total balance for the case of interest that is compounded continuously. The total balance F would be P times E to the I times N. In this equation, F is the total balance after n years. P is the principal, the original money invested in the account. N is the number of years. And I is annual interest rate. To see the differences between different compounding periods, let's see an example. Let's assume the original money is $100. Annual interest rate is 5%. And we wanted to calculate the total balance in the account after 10 years. So in case of simple interest, the equation that we need to use is F is equal to P times 1 plus N times I. If we use the values provided for P, I, and N in this equation, we will get $150, which means that if you put $100 in an account that pays simple interest after 10 years, the total balance in the account would be $150. In case of an account that pays compound interest, the total balance is calculated using this equation. F is equal to P times 1 plus I divided by M to the M times N, where M in this equation is the number of compounding periods per year. If the interest is compounded annually, M is equal to 1, and as a result, the total balance would be $162.89. This value is 8.6% higher than the total balance in the account in case of simple interest. If the interest is compounded quarterly, M is equal 4 because the interest is compounded 4 times per year. And as a result, the total balance would be $164.36. This is the total balance in the account after 10 years. And this value is 9.6% higher than the total balance in the account, which pays simple interest. In case of interest that is compounded monthly, M is equal to 12, and the total balance in the account after 10 years would be $164.70. And this value is 9.8% higher than the total balance in the account that pays simple interest. If the interest is compounded continuously, M approaches infinity, and if we use the equation that we obtained above, F is equal to The principal $100 times e to the I times n. I is 5% and n is 10 years. And if we do the math, we would get $164.87. And this value is 9.9% higher than the total balance in the account with simple interest. Let's recap what we covered in this video. We talked about different types of interest. We learned about simple interest, in which the interest rate is only applied to the principal or the original money in the account. We also learned about compound interest, in which the interest rate is not only applied to the principal, but also it is applied to all the interest previously paid to the account. We learned about interest that is compounded annually, which means that the interest is paid to the account once per year. We talked about interest that is compounded quarterly, which means that the interest is paid to the account 4 times per year. We also learned about interest that is compounded monthly, and in that case the interest is compounded 12 times per year. We also learned that as the number of compounding periods per year increases, the total balance in the account will grow faster. And finally, we learned that in a special case, the interest could be compounded continuously. And in that case, the number of compounding periods approaches infinity. And this is the type of interest that would result in the highest balance. That was it for this video. If you have any questions, please leave them in the comment section below this video, and I will get back to you as soon as I can. If this video helped you in any way, please hit the like button and subscribe if you enjoy our content and would like to see more.